All right, today we are talking about how to classify compounds. And the biggest start is looking at if we have a charged or a neutral species. If it is charged, then we see a very obviously written positive or negative notation. For example, I have cations, which are positively charged species when it says, for example, Na+1. So that's sodium that has lost an electron. Or magnesium +2 ion. So it has lost 2 electrons. Same with aluminum +3, that would be an aluminum ion. Fe+2, Fe+3, ammonium, NH4 +1. Those are all cations because they are positively charged ions that have lost electrons. Or we can have a negatively charged ion. Those are our anions, like chloride, which is chlorine atom that has gained 1 electron, so it's a -1 charge. Or oxygen with a -2 charge, so it has become oxide, so it has gained 2 electrons. Or nitrogen that has gained 3 electrons, so it's nitride, and so on. So notice that there are negatively charged and positively charged ions. Now, if we don't see any charge and we have a compound, we need to look and then classify that compound. If there is a metal or an NH4, which is ammonium, if there's a metal or an ammonium present, then it is an ionic compound. So, an ionic compound, we will then classify as if it's binary or if it's polyatomic. And we'll get more into that in the next video. But biggest thing is there is a metal or NH4 present, it is an ionic compound. If not, then it is a covalent compound. And we are not going to get into this organic piece. That's going to be saved for organic chemistry or biochemistry or microbiology. Those are organic compounds have a lot of carbons and hydrogens like glucose or fuels or alkanes, alkenes, alkynes, fatty acids, DNA, carbohydrates, lipids, proteins. Okay, very large molecules. We are going to focus on, here we go, we are going to focus on the inorganic covalent compounds. And that is, I mean, there will be a few carbons in there like CO2, but it's not lots of carbons and lots of hydrogens. That's saved for the organic chemistry. So we're going to focus on the inorganic. But notice that in our inorganics that the N2O, dinitrogen monoxide, that it does not start with a metal or an NH4. Same with CO2, same with SO3. It would be 2 nonmetals. So let's go back and look at the ions that we were talking about, this piece from the slide before. How do we name ions? Well, when cations pair up with anions to form neutral ionic compounds, we drop the word ion that's on both of their names. But before we get there, I want you to notice that all of these guys in blue are all cations, so meaning that they are all charged ions that are positively charged. And I remember that, I know it's weird, but cat pee, right? Cat pee is disgusting, but it is, cations are positively charged. And how do we know that they're positively charged? Well, because if we look up here in this top right corner, remember this chart? We know that they're positively charged because they're all in groups 1A, 2A, and 3A, or my transition metals, but they have all lost electrons, right? like our video before when we talked about the electronegativity, they have low electronegativity. They don't have a pull towards electrons. They're more likely to give up electrons, right? So they give up electrons, which means they become positively charged. Now, when we name these positively charged ions, notice that the name, if we look at this very first example, the name is just the name of the element from the periodic table, so lithium, and then we just put the word ion. And so it's just the name, this is for cation ions, name on periodic table, PT, plus ion. So lithium ion, sodium ion, potassium ion. Notice that everybody in this black example are all +1 because they are all of these elements in group 1A. They all lose 1 electron, so they all become a +1 ion. So it's lithium ion, sodium ion, potassium ion, rubidium ion, cesium ion. Notice that everybody in this example, except for the aluminum, everybody here are all, notice their charge, are all +2s because they are all in my group 2. So beryllium, magnesium, calcium, strontium, barium all lose 2 electrons, so they become beryllium ion, which is a Be2+ ion. All right, then we have aluminum ion. Aluminum, we jump over to group 3A, so it becomes Al3+. Now, when we look down here at the bottom, we have transition metals, and the charges for some of these may vary. So that is why we see a little bit different here. We have some Roman numerals. The Roman numerals is essentially just telling us, so for example, cobalt and then parenthesis 2. So cobalt 2 ion tells me that it is cobalt with a 2+ charge. Or cobalt 3 ion tells me that it's cobalt 3+. And those Roman numerals are only used for transition metals because those charges can vary. And the Roman numeral tells us its charge. Or if you were to see just the cation name of Fe2+, we would know that that's iron 2 ion. Or Fe3+, its name would be iron 3 ion. So all of our cations are its name on the periodic table plus ion. Pretty easy, straightforward. But then we have, if we look over here at this red group, we have our anions. And notice that these look a little bit different. So for example, if we were to look at this oxide and it's O2 negative. So what we do is we take oxygen right from the periodic table, and now when it becomes an ion and it gains 2 electrons to become a -2 ion, we take the ending off and we add IDE. So oxygen becomes oxide ion, which is, all that's showing me is that oxygen went from 6. It went from having 6 outermost electrons, and then it gained 2 more. So these 2 that it gained then gave it a -2 charge. So it's now an oxide ion. So same with all of, if I go back and look at this top right picture, all of these elements that are nonmetals that gain electrons because they have a higher electronegativity are all going to become anions. So sulfur becomes sulfide, and that's a -2 charge. Nitrogen becomes nitride, phosphorus becomes phosphide, bromine becomes bromide ion, chlorine to chloride, fluorine to fluoride, iodine to iodide. So those are our anions. Again, they are nonmetals that gain electrons, so they become a negative anion or negative charged ion. Now we have another group that's called polyatomic ions, which is a group of 2 or more atoms with an overall charge. And they stay as a group. They're not going to break apart. They're covalently bonded together to keep them as a group. And some examples of polyatomic ions is ammonium, which notice that it's NH4, but then that whole NH4 group has a charge of +1. NH4 with a +1 or a 1+ charge. That's our only example of a cation that's a polyatomic. That's why if we were to go back to a couple slides prior and look at this and say, if it's an ionic compound, it's either got to be a metal or an NH4. That NH4 is, I'm sorry, not there. NH4 is a polyatomic ion that's positively charged, just like all metals are positively charged. So that's our one example of a polyatomic ion that is positively charged. Most of the other ones, and you'll see all right here, are all anions. Notice, see, anion, they're all in red, anions. So they're negatively charged polyatomics, like nitrate. And notice that the endings, if I just had N3-, which is nitride, so it's just a single element whose ending turns to "ide," this is nitrate. So the polyatomic ion is telling me, oh, it's not nitride, it's not just nitrogen. Oh, it's NO3 with a -1 charge. Again, you will have this chart to use so you can help figure out what is what. We also have hydroxide, cyanide. Cyanide is common if you've ever heard of cyanide poisoning. We have sulfate, chromate, carbonate. I'm sure you've heard of carbonation in beverages, pops, and carbonate breaks down to CO2, which is our carbonation bubbles. Phosphate is very common in our biological compounds and DNA. And then we have acetate, which is also a very common polyatomic ion that's found in foods and other ingredients.